Good morning, everybody. I hope you're all doing well on this nice, warm, and summery day. We're now slowly shifting in this course from a few more theoretical backgrounds that I explained in the first half onto actual practical tools that we have recently built using this technology that I just described in the previous individual lectures. And yeah, one of these tools that I want to cover actually in this week is called CogniCrypt. And CogniCrypt is a tool that we have been jointly developing together with other researchers at Paderborn University, University of Alberta, University of Brasilia, and also a few other people from companies actually. And it's about finding crypto API misuses. And I'll, on the next few slides, motivate why this is an important problem and how we are addressing it. So the problem that we worked on, we identified actually already some 7-8 years ago, which is that developers really struggle with cryptography. And you can see from these publications that came out back then that this is really a big problem. So in this study, for instance, researchers showed that about 83% of a number of vulnerabilities that they found with respect to cryptography in general was actually about misuses of crypto libraries. So that means in most cases, when people have vulnerabilities with respect to crypto, it's not that the crypto algorithm or so is broken, it's actually that people misuse it. Then there were other studies that showed, in particular with regard to SSL certificates, that many applications that actually are supposed to validate the authenticity of connections using TLS certificates, they actually fail to do so properly because they are simply misusing certain APIs. And then there was another study back then which showed that also Android apps in particular misuse crypto APIs in almost every single case. And we ourselves actually published a paper in 2016 at our flagship conference ICSI that tried to go a little bit deeper and looked into why is this actually the case, what are developers struggling with. And I will still be talking a little bit about this later. There are also commercial studies that show that this is quite a problem. So this is actually a graphic taken from the State of Software Security report by a company called Veracode in 2017. Actually, I haven't updated this, but I would expect that the numbers still look similar. So Veracode is a company that has a cloud-based SaaS solution. So they do static application security testing, which is basically a fancy word for doing static security code analysis. And they do it in the cloud, which means that there are actually a large number of companies worldwide that send their source code or bytecode to Veracode through their CI/CD chains, and then Veracode analyzes them. And so they have a very good understanding of what vulnerabilities people actually have in their code. And obviously they don't disclose the individual vulnerabilities to other people, but they do disclose statistics about them. And here you can see that actually just after information leakage, cryptography issues are on the second place on their hit list, so to say, of most common vulnerabilities that they see. And when they write cryptographic issues, they actually mean misuses of crypto APIs. So the main underlying problem is that crypto APIs, they're really developed by crypto experts, and well, maybe not even by crypto experts per se necessarily. So we've talked to a number of crypto experts in our collaborative research center Crossing, and many of them are really deeply into the mathematics behind crypto, but few of them actually design APIs. But when they do, they're probably also not the best suited people to actually be designing APIs. So many of these APIs are rather complex because they are coming eventually from these experts. And here, these experts, they talk about concepts that may not be familiar to everybody, right? Such as algorithms and like AES, RSA, or encryption modes such as CBC and so on. And then on the other hand, you have software developers, and they rather want to fulfill a certain task, right? So they want to deal with things such as private data, passwords, data encryption, and so on. And obviously, as you can see, there is a mismatch, right? So here on the right-hand side, you have these high-level tasks and goals and duties. And on the left-hand side, you have these individual cryptographic primitives, right? And the different parameterizations. And it's not immediately apparent what solutions you have to take from the left-hand side and how you need to combine them to actually come up with a solution for a specific task at the right-hand side. And so that's why we also went into this field and actually conducted this first study at ICSI 2016, where we really looked into why do Java developers, so in particular Java developers here, struggle with cryptography APIs. And basically we looked into application developers, right? And like I told you, they have certain specific tasks that they have in mind. And they have to worry, though, about all these different questions here, right? So what could be an optimal key length for an algorithm? What actually is an encryption mode and what is the right one for me? When should I actually use encryption? When should I use hashing? As our study showed, that's actually not always clear to programmers. And if you do use hashing, what kind of hashing should you be using, for instance, right? And this is just one selection of questions. There are actually many more that are important in this space. And so we looked into a number of different questions in this study, but one in particular that we asked them was which method and tools would actually help developers with crypto usage. So we asked the developers themselves, and these were developers who we actually knew had previously developed with cryptographic code. So we asked them, what do you think, what kind of tool support would actually be able to assist you? And so one thing that they said was, okay, better documentation would really be important. So they wanted to have better documentation with examples. In particular, as you can also see here, examples were mentioned quite frequently. Then they wanted to have best practices and high-level, high-quality Java doc and so on. But the problem with this is other studies show that yes, you can have better documentation, but first of all, you need to keep it up to date, which is something that's really hard to do. So there is a lot of documentation on the Java cryptography API, for instance, but typically a lot of it is already outdated by the time you read it. And the larger problem, though, is that typically this is not read, right? So for the case of Java, if you look into the documentation of the Java Crypto API, the JCA, if you were to print it on A4 paper, it would be about 70 pages long, 70 pages, right? So that's quite a bit. And almost no person, I think, who uses that API has read it in full. And by the time you've read at the end of it, you've probably already forgotten the the start, right? So that's I think it's somewhat wishful thinking, right? So better documentation might certainly help to some extent, but personally, I don't believe it's the right solution. Then another interesting idea that people had was a higher level of abstraction. So if developers actually want to implement certain tasks, such as encrypting a file or authenticating a user, why not give them APIs that do exactly that, right? So why is there no file encryption API, for instance? And I think that's a fair point, right? So there can certainly be APIs that fulfill a number of these frequent tasks, let's say, although we also saw that, just by looking at some of the crypto implementations that people have, fairly often, at least in a large minority of cases, let's say, they also have tasks that don't fit a general pattern, right? So by having such more high-level APIs, you can probably get around securely implementing a large number of cases, but certainly not all of them. So that would be helpful, but it wouldn't cover all the different situations. But there are people working on better APIs, and I think that's definitely a useful endeavor. So that might be a solution, but rather a long-term help, right? Because these APIs need to be written, they need to be secured themselves, they need to be established, and they need to become popular in the community. Then also, what is probably more interesting to us, because we develop a lot of different tools, as you know, based on static analysis, was that people wanted to have different kinds of tooling, right? So they said, okay, it would be nice to have a testing tool that identifies configuration mistakes, weak algorithms, or some IDE plugin to generate code patterns for specific use cases. Again, templates for common usage patterns, and a crypto debugger. And so that would then really help them basically close this gap, right, between the high-level tasks on the right-hand side and the low-level things on the left-hand side, because, for instance, using a static analysis, you could check whether you're doing any mistakes regarding these low-level APIs on the left-hand side, or maybe using a code generation, you could even generate secure code for these tasks that you have on the right-hand side. And yeah, so we actually implemented first a prototype tool, which is now actually slowly being brought into a more commercially ready state. And this tool is called CogniCrypt, and today I want to talk a little bit more about it. So actually CogniCrypt combines both of these ideas. It allows you to do code generation, so you can actually really generate provably secure crypto integration code for a number of different use cases, such as authentication, file encryption, and secure connection establishment. But it also implements a really rapid and highly precise static analyzer that uses a lot of these concepts that I have explained in the previous weeks to make the analysis precise and efficient. And this analysis then allows you to identify crypto usage mistakes. And this is this static analyzer that I want to focus on in this lecture today for obvious reasons. So to show you a little bit of the kind of misuse patterns that we need to cover, let's take a look at this particular example that you see here. And that is an example on password-based encryption, PBE. And if you want to do password-based encryption in Java, you're supposed to use such a PBE key spec. So that's a password-based encryption key specification. And what this does is it will hash your password a number of times. And typically this is done in many different rounds and using a salt. So you're using a salt to actually make the hash unpredictable. And you're using not just a single round, but usually many rounds. So the BSI actually recommends 10,000 hashing rounds to make any possible reconstruction of this of the original password from the hash even much more unlikely, right? Because then if you want to compute rainbow tables or so, as an attacker, you have to go through all these rounds as well, and they cost a lot of time. Now, this is code that we actually found in a real-world Java application using our tool. And if you know a thing or two about cryptography and hashing, you can see a number of different mistakes here, actually, that we would like to identify using our static analysis. So first of all, whenever you have a salt, it should actually be random. It should be securely randomly generated, which this is clearly not. It might have been securely randomly generated at some point, but then it's fixed and it's put into the code, which also makes it appear in the bytecode, and that means any attacker can easily extract this. So the salt is rather worthless here. So the fixed salt is never a good idea, and in particular having it right in the source code is not a good idea at all. To figure this out, that we actually have a fixed salt here, we already might require some sort of field-sensitive analysis, right? Because We might want to distinguish that field from others to actually have a precise analysis here. And the sort might not always be defined as nicely directly in this class. So field sensitivity might be important here. Then also, like I told you, this is actually the number of rounds that is specified. And like I told you, this should normally be above 10,000. And here the programmers only chose 20, which is better than 1, but it's certainly not sufficient. So we want to have a static analyzer that can identify such constants as well. And often actually with these crypto APIs, the constants are directly at the right call site or at the constructor call here, as you see here. So typically the analysis is rather simple, but it might not always be the case, right? So you might have some intermediate assignments of this value to variables or fields and so on. Then also, that's not a good idea what you see here. The password that is actually being passed to this particular method, it's being passed as a string. And storing passwords as a string in Java is never a good idea. You may wonder why. Well, in Java, strings, they are always immutable. So that means they are specially treated by the Java runtime and by the garbage collector. Namely, if you are to create two identical strings in a Java application, then typically these strings are pooled. So that means these two formally, non-identical, but actually equivalent strings, they are made identical. So they're really using the same object to represent them. And that means that quite often these strings are actually sitting in memory rather long. And so you might have heard of things such as cold boot attacks and so on, where people actually try to extract password data out of the raw memory of the process. And for that reason, passwords should never be stored as a string, but they should rather be stored as a byte array or character array, so that you can actually null out these arrays explicitly after they have been used, so that you can get rid of this password data as quickly as possible and it's not sitting in memory any longer than needed. And so these kinds of type constraints here we want to be able to identify as well. And yeah, so we have actually developed this CogniCrypt project, and you can take a look at it yourself at this particular URL here. It's an Eclipse incubation project, so it's part of the official Eclipse open source infrastructure. And right now you can also download and use it with Eclipse. We are also working towards solution for other IDEs, IntelliJ in particular. So stay tuned for more on this. We had a number of design goals when we started implementing all of this. And first of all, we wanted to have an efficient and precise analysis to actually detect misuses of these crypto APIs. But we also wanted to allow for easy and quick customization to actually support these new crypto APIs. And in order to allow this, we actually implemented a novel domain-specific language called Crizzle, Crypto Specification Language. And I will present the basics about this here, but if you are interested in more details, we actually have an eco paper about Crizzle, and actually also more recently a journal paper about this, where you can actually read up all the details like syntax, semantics, and so on. Here I want to explain it just using an example. And yeah, I'll give you a couple of seconds to actually take a look at this code. So this is code that is supposed to be written ideally by people who have developed the crypto API themselves, or at least by experts who really fully understand the API and what the different constraints are that you as a developer should adhere to when using that API. And this is the first half of a typical Crizzle specification. And what you see here is first of all a header that tells us for which particular Java class we are now writing the specification. And there is a Java API called key generator, and we are now here specifying its usage rules. And these are not misuses that we specify, but this is rather a whitelisting approach or an allow list approach where we actually tell the tool what should be allowed, what are correct uses of the API, and CogniCrypt will then faithfully reject or flag any deviation from this norm. Here in this objects block, we actually define a number of helper objects, or can also be primitive values like you see here, by just giving them a name and stating their type. And then these identifiers can be used later on here, in particular also in this events section. And here we name, and we also give a name to a number of different events that are relevant to the specifications. For instance, on key generator, you can call these get instance methods to actually generate a key generator. And then the first parameter to get instance here would actually be a string, which you can see here, right? And it's not just any string. It's actually a string that defines a key generator algorithm. So that's why we gave it this name, right? So, but we could have given it any name, right? So this has no semantics on its own. It's just, to make the specification more easily readable, of course, you should be choosing sensible names. There's also a constructor that takes 2 parameters, but the second one doesn't matter. So we omit this here. We only care about the first. And we name these events G1 and G2. And then you can have these accumulator or compound events here. So we can write get instance in capital letters whenever we mean either G1 or G2. Okay, so this you can read as set union. Similarly here, we care about initializers. And then there's also eventually a gen key or generate key event where the programmer actually calls the method generate key, and that returns a key, which makes sense for a key generator, right? So we have the specification here that involves these values and these events. Now the second half of the specification is where it gets interesting, because now here we can actually define constraints over this key generator. And there are 2 different kinds of constraints that we allow. One are event ordering constraints. So they basically tell us in which order these different events that we just defined need to be invoked on this particular object for this use of the object to be valid. And this is basically a regular expression, and this one would tell us that you must call get instance initially, then you may call init, it's not necessarily required, but then you must call generate key, okay? And this is really a general regular expression, so you can also have a star to repeat things and so on. Some API constraints are a bit more complex than this one, but I guess you get the gist. And then also down here, you can actually have what we call parameter constraints. So they tell us what are the valid parameter ranges for these different values that we have at these different events or API calls. So for instance, one possible restriction here might be that the algorithm must be either AES or Blowfish, and then depending on what algorithm you chose, you can actually have such an implication, and you can say that the key size then has to be one of these, for instance, right? And this is just a simplified example. If you look into the real-world APIs and our real-world specifications, which we have online at eclipse.org, you will find that they are actually somewhat more complex. Well, not in the sense that they necessarily use many more constructs, but there are just many more choices, right? And also these regular expressions, like I said, they can look more complex as well. Yeah, and then we still have some rely guarantee reasoning that we implement down here. So for instance, the key generator specification, when all of this is fulfilled, so when you have a correct and secure use of the API, you can actually generate such a predicate here. So this is saying when all of this holds, this ensures that we have securely generated a key, namely this key, right? So this is the key variable that we defined on the previous slide for the final gen key event here that will generate this key, and we are saying if all of this holds, then this is not just any key, but it's a securely generated key. And then other specifications, as you can see here, they can require this, right? So, for instance, the signature specification can require that you have a securely generated key, okay? And this actually makes a lot of sense, right? Because this way you can bind these specifications together, and for instance, the signature can tell that it has only been correctly used if it has been used with a key that has been securely generated. Okay, so this way you can compose these different individual class-based specifications together. I'll get back to this on a slide a little bit later. And then we have this general CogniCrypt workflow. So the idea is, like I said, you have some expert that writes these quizzle specifications. And then we have the CogniCrypt tool, which we wrote. And using these specifications, the tool is parameterized to actually give you a customized static application security testing tool. Okay, and that's nice because the tool itself doesn't need to be changed when the API changes. The only thing you need to change is the quizzle specification. And then once you have this tool, you give it any Java application, or in our case also actually any Android app, and you can just run the tool over this application, and then you get a report that tells you what the different API misuses are and how they should be fixed. And we have a nice IDE integration for this, so you can run this headless, so as a command line tool, and we are frequently doing that on thousands of different applications. But you can also use it within the Eclipse IDE. And in the next video, I want to give you a brief demo of what this actually looks like. See you then.